Okay, well, thank you. And thanks everyone for staying till almost the very end. I know you're probably getting a little bit tired, but I think this will be an exciting panel, so I do urge you to stick around. We have some great panelists today, and what I'm going to do is I'm going to start and ask each one of them to introduce themselves. And just go down the line here. I want you to start, Ish, and introduce yourself and your company.
Okay, thanks, Doug. Hi, everyone. My name is Ish. I am the CEO and co-founder of QC Design. We are the fault tolerance company, and our focus is on helping quantum hardware manufacturers get to fault tolerance. And we do this by providing design software and architectures for fault tolerance. And by design software, this is the bit I want to talk a bit about today. Roughly speaking, this is like the AutoCAD of fault tolerance. And it's software that helps you understand the performance of your logical qubits in the presence of realistic hardware imperfections. Such software is really important if you want to start showing the first logical qubits in the lab, but also if you want to design architectures for fault tolerance. And very mature teams already have access to such software in-house. I'm thinking about Google and Quantinuum and PsiQuantum and Xanadu and so on. But they've put in a lot of effort and time into building such software. A vast majority of quantum hardware companies do not yet have access to this. So what we do is provide access to such software, industry-grade software, with a simple software license. We are at the very early stage, around 10 to 15 people. Just had our first customer sign up last month, very excited about that, and learning from our customers what they're looking for and trying to build that and help them towards fault tolerance.
Okay, thanks, Ish. Tommaso.
Sure. Hi, everyone. Good afternoon. Thank you for coming. I cannot really see any of you because of the lights, but I can feel somebody's in the audience, which is great. My name is Tommaso DeMarie. I'm the CEO and the co-founder of Entropica Labs. I have a background in quantum information theory, and we started the company in 2018, so we've been around for quite a while. We are based in Singapore. We are purely a software company, so we don't build any hardware. And the problem we are tackling is the following problem. We start with the assumption that we are going to need fault-tolerant quantum error correction, most likely, to produce commercial value from quantum computers. But the very interesting problem here is that even if tomorrow we were to have a million physical qubit machine, it would be very hard, possibly impossible, to go from the theory of error correction to practical implementation of error correction codes. And the issue is that we are still lacking a programmatic way, programmatic way to design, to implement, to verify, and to test and run error correction codes on multiple quantum computing architectures. And this is the focus of our work at Entropica. We are building software development tools with the initial scope to design, handle, and test error correction codes on quantum computers. We just closed a funding round, so we have runway for the next few years, and very happy to be here today. Thank you.
Okay, thanks, Tommaso. Julien.
Thank you, Doug. Pleased to be here today. So I'm Julien Camirand Lemyre. I'm a co-founder and CTO at Quantique. So Quantique is a quantum computing hardware company that focuses on quantum error correction and fault tolerance. The work we've been doing is basically building a superconducting architecture, focusing on a new type of qubit, which is basically bosonic codes. And the reason we are doing this is because these bosonic codes also can be error corrected by themselves. And this has been the main focus of the work we have been doing since our creation in 2020, basically demonstrating single qubit that can be error corrected and showing performance on error correction that is starting to be interesting. So I also encourage you to look at our recent paper, preprint and archive on this, where we actually demonstrate the capability of this platform. And the focus of our company is really hardware, meaning that we focus on development of the hardware, of course, but also integrating quantum error correction at all layers, so in single qubit, as I just mentioned, but also developing the architecture for a full-scale fault-tolerant quantum computer.
Okay, thanks, Julien. And Steve, last but not least.
Hi everyone. So I'm Steve Brierley, the CEO and founder of Riverlane. So we're working on error correction as well. We are a chip design company essentially. We're classical chips, so no qubits on our chips at all. We're based in Cambridge, UK, about 100 people, because Cambridge, UK has this great expertise in chip design. So ARM's headquarters is there, and so the reason why we need to design specific chips for quantum error correction is that this is fundamentally a real-time data processing problem. So coming out of the quantum computer is your syndrome data. You need to process that before the next logical operation. And if you don't, the quantum computer is just going to grind to a halt. So in solid-state systems like superconducting or silicon-based quantum computers, this syndrome generation rate is on the order of megahertz, so a million times every second. At a million physical qubits, we're talking 100 terabytes per second. That's the same as Netflix global streaming. We need to solve this problem in a room, in the same space as the quantum computer. So we're designing dedicated chips to do that. We released our first generation over the summer. It supports 1,000 physical qubits and solves the decoding problem at megahertz, so at faster than megahertz, so 240 nanoseconds. And that's the readout, correct, decode, correct cycle. So this is really the clock cycle of the quantum computer, and really excited to be working with lots of the companies developing quantum computers around the world with different qubit types to integrate this.
Okay, thanks, Steve. So we had worked out some questions a couple weeks ago before any announcements were made this week. So if you see any similarities, it's all coincidence. And the first question, which I will start and ask Ish to be the first responder, is, looking back in 2023, what demonstrations or what type of things, advancements have you seen in error correction that you think are notable?
Yeah, thanks for the question. I think I want to look at 2022 and 23, where Google demonstrated a true logical qubit, and also now Quantinuum demonstrating operations on logical qubits, and then looking at Quera's demonstrations recently. So it's this stream of demonstrations from different platforms, all of them thinking very seriously about first logical qubits, first magic gates between different logical qubits, and also large-scale computation on logical qubits. So I think demonstrations of error correction are getting more sophisticated by the day. I think this is a real transition time for the industry.
Okay, anybody want to add to that? Okay, go ahead.
Yeah, I actually would like to add a thought on that. So one of the theses that I had a couple of years ago was that with time, like early enough, we would have started to see more hardware companies that from the very onset, they would focus on building, let's say, fault-tolerant quantum computers, or starting with a design or with an architecture that has quantum error correction in mind. And I mean, Julien here from Quantique is a perfect example of that. In fact, we are seeing more of these companies. I can think of like Universal Quantum, for example, them, Alice and Bob. It seems to me that they are coming on stage, and from the very beginning, they're saying, we are thinking about how to minimize errors, how to bias errors, or how to think of simpler ways to implement error correction on our machines from the very beginning, which I think is really, really exciting. And I believe they've learned a lot from what has happened in the last 10 years in terms of hardware manufacturing. And I also think is a sign of maturing ecosystem, and also, I guess, a sign of the industry realizing or simply coming to accept how important it is to aim to fault-tolerant quantum error correction in the long run.
Okay. So error correction actually requires expertise and technology, both in hardware and software. So we have a mixture in this panel, by the way, which I think is good. But let me start with Steve and ask Steve, what do you think are some of the biggest challenges of implementing a fault-tolerant computer? Why don't we have them today?
We need to improve the physical error rates. So we have to get below the threshold, of course. And to do that while scaling up. And that's really what's hard about it. So we need to go from hundreds of qubits to hundreds of thousands of qubits. I think from the error correction perspective, the goal of the error correction community is to make that easier. So to figure out how to take advantage of the specifics of the errors that are inherent in the physics in the quantum computer. And we've shown that if you can do that, then you can lower the overhead of error correction. So you can reduce the total size of the system you have to build to really do something useful. And then the last implementation challenge is of course doing this all very quickly. And I mentioned this already. I think if we have to solve this problem very, very quickly, it's a real-time data processing problem. So Barbara Terhel coined this phrase of the backlog problem in 2015 and pointed out that if you don't solve this problem, the whole system grinds to a halt. So I think another big breakthrough in error correction has been showing how to overcome that backlog problem, at least in theory, and now we have to go build a multi-core decoder system.
Okay. Any other guys see other challenges that you want to mention? Yeah, go ahead.
I think first I would agree with you on the challenges of the hardware perspective, mainly on understanding noise and building error correction codes that are tailored for the noise you actually have on the chip. This has been mainly our focus at Quantique, trying to do this and correct for our error, which is photon loss basically on the chip. But scaling the architecture, I think, requires a lot of development both on the code side. Things like LDPC codes are super interesting, but it's super challenging also at the same time for hardware companies, and long-range coupling, for example, will be something that we will need to have on chips in order to unlock not only these codes but also systems that truly scale in a fault-tolerant manner.
Okay.
Can I add one more point on that? I agree with everything that has been said, but I'll also make another example. So a couple of months ago, there was the IEEE conference in Seattle, and with other colleagues, we organized a mini workshop on the future software stack for fault-tolerant quantum error correction. And a lot of people came, and what I still think is really interesting, like part of the challenge with the work that also we do at Entropica, is that it remains very much unclear how that software stack is going to look like. There's a lot of open questions, which I think is great personally. So one more challenge that I will add to the bucket of challenges that we already have is how are classical and quantum computing systems going to work together with the problem of having to do a lot of the work in real time, and how we can build the software to do all of that in parallel. I think this is an incredibly big challenge, and it's becoming more and more apparent.
Yeah, and of course there's people working on it. I think Steve will tell you a little bit about his chip maybe after this session. But one thing we're hearing, at this conference is a lot of stuff that can get pretty confusing. You have error correction, you have error suppression, and you have error mitigation. And for a layperson, that might be very confusing how they work together. Tommaso, maybe the question I would have is, can any of those three different areas of technology, can those work together possibly to get improved results?
In fact, we can make things even more confusing. We can also add error characterization, which maybe sits even lower, right? So you want to characterize the errors, you want to suppress them, you want to mitigate them, you want to correct them. I would say the following. I think it really boils down to cost benefits at the end of the day, right? So all the methods that we are discussing, they have resource costs, with error correction being the most cost intensive, but also the one that ideally gives you the highest benefit, right? Because you can correct the errors. Error mitigation is an interesting one because it works really well at small scale, but at least on average, it tends to have like a cost that grows really, really quickly up to exponential if you have much larger sizes, right? So what I would say is that it will all boil down to cost benefits. At some point, error correction is going to take off once we have systems that are large enough and that have low enough error rates, then the main actor is going to be error correction. But I also believe that being able to characterize noise on the device very well, and I think, Steve, you basically just said that, will help with the implementation of error correction, because then you understand better what happens on the machine, and you can tailor your codes to the performances of the hardware. I do believe that error suppression will stay. Like, for example, dynamical decoupling, there's no reason why you wouldn't want to do that, even in an error-corrected system. The lower error rates you have, ideally, the better your error correction code is gonna perform. So to try to summarize that, I think, especially at the beginning, you will see all of these techniques being mixed together. And eventually, error correction, I believe, will be the main actor. And if any of the remaining ones can support error correction, then people will do so. They will find smart ways to integrate all of that.
Comments? Yeah.
So maybe something that is interesting is also learning from all these techniques. Both for error mitigation and also error correction, things that will be important are things like compilation. So how do we compile these systems so that we can get the best out of it, get the less amount of errors? And I think there's a lot to be learned from each of these techniques, even if they don't work in parallel, for example.
Okay. The other thing that, I see, which can be sort of confusing, is that there's all these different algorithms that people are using: surface code, color code, GKP, quantum LDPC, bosonic codes, all that type of stuff. And I'm going to ask each of the panelists if they have a favorite, and whether or not they think that, like many things in technology, at some point it'll be one where one dominates the industry. And I'm going to start with you, Julien. Do you have a favorite code that you like?
Of course, I'm very biased here, so
Yeah, that's why I asked you.
So our favorite code, of course, is GKP code. So this is what we've been doing since the beginning at Quantique. But we also think this code might not be working alone in a fault-tolerant perspective. So each of our qubits are GKP code by themselves, but we can concatenate these codes into an architecture. And what is the favorite code for the architecture? I think it's a question of roadmap. Of course, I think everyone is looking forward to these scalable code, which is LDPC codes right now. There's also interesting work by IBM showing actual code that could be implemented on a system. But before we get there, we actually have to do the steps to get there. And I think this is where the other codes are also super interesting in terms of learning how to do quantum error correction at scale and understanding what are the challenges to which code we should be moving forward as we build the architecture.
Okay. Ish, what's your favorite?
Hard to answer. I would say that every different platform comes with its different constraints and its different advantages. Some platforms allow you to levitate your qubits. Others, you can have things which are much more planar, or qubits that are connected with long-range photonic interconnects. All these different platforms also come with different kinds of noise. So I think it's really an important journey that we're all on in terms of finding what's the best error correction method that works for the constraints, for the advantages, for the noise in each different platform.
Okay. Tommaso, favorite?
I don't think I have a favorite one. So I can go with that, or I can say, obviously a lot of attention has been paid to the surface code. Yeah. I'm not sentimentally attached to that, but it's an incredibly neat architecture, and I think it goes to show the ingenuity of the people who work on error correction is really beautiful. Whether it's going to be the only, I think you hinted at it in the question, whether there's going to be only one code at the end of this journey, honestly, I don't know. Today, and I'm happy to change my mind at any point in time. Today, my feeling is that different platforms might serve different purposes, or different architectures, different computing architectures might serve different purposes moving forward. And if that's the case, it is very likely that different codes will come or will become tied to different computing architectures. I don't think that will be surprising in the short term. Which I also think is incredibly exciting, because as Ish was suggesting, it gives us so much space and so many opportunities to really understand how the performances of the machines influence the performances of the codes.
Okay. And finally, Steve.
Yeah, so there are really three things that matter in error correction or in choosing the right code. So, one is the connectivity, so like which qubits can interact with which other qubits. The other is the threshold, so kind of how good do your physical operations need to be before the code's actually beneficial. And the last one is the overhead, so how many physical to logical qubits do you get? Now, I think kind of myself and Al Campbell would say the same. We've been trying for a very long time to beat the surface code, and in a way, the simplicity of the surface code is kind of remarkable. And I think one of the reasons why it will be the first code, very likely, that's implemented. So even on the route to doing something more exciting like a quantum LDPC code, you may as well do the surface code anyway. Because it has an easier to achieve threshold and easy to architect connectivity requirements. And so I suspect that's what we're going to see in the first generation of error-corrected quantum computer. Of course, there's loads of great research that is happening around other types of code and improving some of these other metrics, but they really all have to come together. So I'm afraid my favorite is still the surface code, and it has been for 2 decades.
Okay, well, we'll have to see how it all works out. So the other thing that, sometimes people get the impression is that there's essentially 2 types of quantum computers. There's NISQ and there's fault tolerant, and that there's going to be a step function when you go from one to the other. Ish, do you think that's going to happen like that, or do you think it's going to be sort of more of a gradual transition where maybe people start implementing fault tolerance, but it's not a perfect logical qubit?
Yeah, I think Tommaso already touched upon this, that there are many companies that are aiming straight for fault tolerance, including Not Quantique, Alice and Bob, and others. But I want to mention that there is a reason why it makes sense to focus on one or the other. Developing for NISQ is very different from developing for fault tolerance. It's not merely about having lower error rates. For NISQ, you need lots of different kinds of gates, or you need different kinds of connectivity. For fault tolerance, you need a few types of gates that you can run again and again and again with the right kind of noise. So if you're able to identify what are the right gates, what are the right noise, then you can move much faster towards fault tolerance. So I expect that there would be development lines within companies or companies focusing on development entirely, which would focus on NISQ, and other development lines focusing on fault tolerance. And these would be devices that would start to diverge more and more in the coming years. Very different looking fault tolerant quantum computers from NISQ computers in 2 to 3 years. That's how I think about the future.
Okay. Go ahead.
So I think fault tolerance is definitely not a step function. And the reason is that we need to run experiments in order to develop the next generation of error-corrected quantum computers. So we need to understand the noise and what's happening in the system. And so kind of what you've seen this year of early implementations of parts of the fault-tolerant stack are doing exactly that. Like we're building prototype logical qubits. Of course, that's not the full thing, but you understand then more about how are the errors showing up in the syndrome data. So I see this as a gradual increase in capability to early fault tolerance that will be on this journey for the next few years. So yeah, definitely not a step function.
Okay. So let me ask Tommaso, since you're a software person, what do you think are some of the most important improvements that we need to see on the hardware in order to really implement fault tolerance? You can't say they're all important equally.
No, I mean in a way they are. Okay, maybe this is a trivial answer, but it's a little bit like when you go and buy a computer, and if they tell you, do you want more RAM? Do you want more computing power? Do you want more space on your memory? Like, sure, I want all of that. So it kind of ties back to I think the first question that you asked, right? What is missing and what do we want? What do we need? We need more qubits. We might need, well, we need more qubits. We need lower error rates. Like ideally, if I could ask for anything, I think having as low access as possible to the functionalities of the device is very useful. I really don't know how this is going to look like in 5 years, but we might see a tendency from hardware companies to shield from users what is actually happening in the background, both at the quantum and at the classical level. And I think that actually raises the very interesting question of how easy or difficult it will be to run all sort of experiments, not only error correction on machines, if you're limited on what you can actually control from the outside. So maybe a different way to answer your question beyond the more banal observations of better qubits, more qubits, and more control. What I certainly like, what I love in fact, and what I appreciate from the hardware companies is when we are given the opportunity to collaborate very closely with them and get a better understanding of how the systems are performing, for example, what kind of noise they see, also what they want to demonstrate. So I guess another way to answer your question is having tight collaborations between again, a bit of a maybe simplistic way to say it, between the hardware companies and the software companies, I believe is going to be incredibly important moving forward in error correction. Also because at the end of the day, the hardware folks, the folks who build the machines, are the ones who understand the machines the best. So I think that is really, really crucial.
But they need the guidance from the software people to optimize their architecture.
Exactly. Yeah. So I mean, maybe that sounds. I think a lot of hardware folks would say, no, we don't. We know what to do and how to do it, which in some ways is fair. I think what we can contribute from the other side is with useful tools to make their work easier.
Okay. Anyone want to add to your list of Christmas wishes for the hardware companies? Okay. So, you were talking earlier about all the advancements that have been made in 2023, and certainly there's been a lot. You guys have maybe some visibility in terms of what we should look for, things that we might expect to see in 2024 that might continue the progress we made in 2023? Maybe Steve, you could start with that.
Yeah, so start to see people doing logical operations, and of course the Harvard papers doing exactly that. So yeah, even performing a Hadamard gate on a single logical qubit is interesting. So that's the next great experiment. We'll see kind of more experiments on different types of qubit or by different groups doing logical qubits and kind of understanding more about what is it that's bottlenecking the system to improve the performance. So I really like the way the Google team presented their results of like, here's the lambda, here's how the code is showing suppression of errors. I think the next things to come then are sort of small logical operations. So ultimately scaling up to, and perhaps not next year, but the year after, kind of doing tens of logical qubits, tens of operations on logical qubits.
Okay. Any other comments?
Yeah, maybe I would jump in on that part. I think this is super important, and this is where we are going. For example, at Quantique, this is our next step, basically realizing gates between error-corrected qubits. But I think another point also is metrics around quantum error correction, logical qubit, and these kind of things. And something that we are looking forward also is benchmarking gates on error-corrected qubit and seeing also the lowering of the error rate of these gates. So I'm really looking in that direction as well.
Yeah, nothing makes me happier than seeing logical qubit demonstrations. We've seen different platforms do this. There's still some platforms for which I think we're holding our breath. Photonics, spin qubits, cat qubits. Would love to see 2024 give us some logical qubits in also those platforms.
Okay.
I will make I will make two comments. I'll add a little bit to what Julien was saying. I think it will be great, and in fact, I agree that we're going to see more of that. I was going to use the word standards, which is maybe too much in the short term, but really having a better way. I think folks sometimes ask, how can we understand the value and the also the magic of different experiments in error correction? How do we compare Google's experiment with the Harvard results? Is a good question, and it's not so simple to actually answer that without going very easily or very quickly into the technicalities of the experiments. So I agree, it would be great, and I think it will happen, to see better standards, better benchmarks, and better apple-to-apple, I guess you can say, comparisons between different experiments. I will also say that I expect next year, maybe next 2 years, are going to be there will be a lot of results, I believe, from trapped ions and neutral atoms. I mean, it has already started now, right? And we're going to see more of that because they have really good fidelities. They're starting to get, the arrays are starting to get pretty big, incredible control. So these are all good ingredients for strong demonstrations in error correction in the near term.
Okay. So, as we all know, I think in the quantum world, of course, you have the hardware, but there's also some pretty good quantum simulators or quantum emulators that will emulate what's happening in the classical, on a classical computer, what the qubits do. As you guys are developing your hardware and developing your algorithms, how important is a simulator that can simulate the error correction? Or do you really need to work hands-on with the quantum hardware just because the simulators can't capture exactly the way the hardware reacts? And I'll start with Julien and see if you have a comment on that.
Yeah, I think it's a real challenge, especially for us. So the way our qubits are built is basically they embed redundancy directly into it. So we're using basically multiple photons into superconducting resonator, which is, on the other hand, super hard to simulate, and we cannot simulate large systems. And in that perspective, for us, the challenge is really to understand the physics behind the noise also, so that we can have better models that could fit into the error correction codes that are larger scale. So really, these software are very important for us, and what we are looking for is really getting into approximation of the noise models that can be simulated at larger scale to build the architecture, basically.
Okay. Anyone else comment?
Yeah, maybe I can go there. What you cannot simulate, you cannot design. And I think this is really a big problem in fault tolerance. The problem starts already at the lowest level in terms of, for example, bosonic modes like GKP qubits, or even in photonics, understanding the many different degrees of freedom of light, or neutral atoms with so many different electronic levels, simulating that, turning that into thousands of qubits that are needed for fault tolerance. I think this requires not one simulator, but many different simulators that talk nicely to each other. And once you have these simulators in place, you can then choose, okay, this is how the future architectures would look like. So I think simulators will play an increasingly important role in the coming few years for designing for fault tolerance.
Okay.
Can I add a point on that?
Yeah.
In fact, I'll go back to the Christmas wish list.
Okay.
In fact, maybe without focusing on the simulators, I'll focus more on the devices. Now that we have increasingly more complex devices, which I think we can argue are, some of them are already beyond what you can simulate with classical computers. I do actually believe that it's going to be crucial to work as much as possible on the machines. And it goes back to what Steve was saying, right? This is true with classical computing, and it will be true. In fact, it already is true with quantum computing. Each generation of machines is driven or inspired by the previous generation. So you learn, you adapt, you improve, right? So another maybe item in the wish list is quantum computing time. What do we ask? Or how can quantum hardware companies, support the development from all sides? Is making their machines available and also be generous with their availability.
Okay. Yeah, that's important too. So, when I talk to people, and we talk about performance measures for quantum computers in general, they talk about coherence times and gate fidelities and that type of thing. And what is not quite talked about as much, what I think it should be talked about more, is actually things like the gate time, the time that you actually can process an algorithm, because it varies by orders of magnitude depending upon the technology. Steve, when people move from a let's say NISQ level machine with no error correction to something that has error correction, is there a lot of basically, I will call it a slowdown in terms of the time it would take a physical gate to do something and the time it would take a logical gate to do something? Do you think that that's going to be significant, and do you think it's going to be important?
Yes, there is. So so you're doing multiple physical gates to measure your syndromes, and then you're repeating your syndrome measurements many times, and that all wraps up into kind of how you implement logic. So yeah, there's a fairly big overhead to adding error correction, both in terms of physical qubits, but also clock speed. And yeah, as you said, like different qubit technologies have different physical speeds. I would say though, there is quite a bit we can do in terms of parallelization. So I suspect this is really a trade-off between number of physical qubits and their raw clock speed and their connectivity. I think these three things will be traded off against each other, and then it will come down to feasibility and cost of building the system that will be the driving factor. I think the first error-corrected quantum computer will probably be really slow, but who cares? Because it's like really hard to do that. And then second generation, sure, we can really work on speeding this up.
Okay. Any other comments? Okay. Well, we have a couple minutes left, so we can take some questions from the audience. And the only problem is the lights are shining in my eyes, so you guys are going to have to help me. If you have a question, maybe just, I guess, shout it out, and we'll take it.
Yes, so the first large-scale quantum computers, like optimistically, they can run algorithm in hours, days, weeks. It means like they're going to be able to run like maybe a few thousands at most calculation per year. Should they be designed to be application specific from the ground up?
Application specific from the ground up.
Yeah, so the only thing that the quantum computer is doing is syndrome extraction, right? So the only thing the physical system is doing is error correction. How you implement logic is done via decoding. So there's only one application for a quantum computer, that's error correction. How you use those quantum operations, well, that's up to you. I think the first major milestone will be 1 million quantum operations. I think that's actually achievable with on the order of 10,000 physical qubits. And there are a number of approaches that could do that, and I think that's really exciting.
Okay. Anything else? Okay. Did I see something back there on the left? Yeah.
Is there a fidelity gate level from which error correction is no longer possible?
You wanted a target fidelity level?
Is there a fidelity level of the gates like 95% or 96% under which the correction algorithms don't work anymore or are not useful?
Yes, so you need to be below the threshold, which is around 99.9%-ish. So you want to be sufficiently far below that threshold.
Okay. Just to wrap, one more question. Okay.
Oh, sorry, if there's time for one more.
Yeah.
So you guys talked a lot about designing codes specific to the hardware, which I agree is super important. But what do you think about designing codes specifically for the application or algorithm that you're trying to run? Like ones that allow the most efficient realization of the gates that are required? Just wondering if you guys have any comments on that.
Yeah, I think the short answer is no. You want to design the code like if you can get error correction to work, that's the massive achievement. You don't want to have another constraint. I mean, you need your code to be able to implement all of the logic, but it doesn't really matter if you can do it, you know, as long as you've got a universal gate set.
Okay, well, thanks so much, guys. Let's give them a big hand.